All right, welcome to lecture number 6. You will be pleased that this one should be a lot shorter than the other ones that we've had, as we're just going to be focusing on the chi-square test. Up until this point, we've talked about testing differences between groups, whether it was 2 independent groups or 2 dependent groups, or a sample to a population, or more than 2 groups. But in this lecture, we're going to be talking about what do you do when you want to test relationships between categorical variables. All right, I really shouldn't have to do a video for this slide. This should be an old hat for you. This is the same process that we've been going through, that we went through with all the tests you learned about last week. But remember that this process is the one we engage in when we're hypothesis testing. So we have a sample, but we want to make inferences for a population. So we state the null hypothesis and an alternative hypothesis. We test against the null. We choose a test statistic, an appropriate one for the data that we have and the question that we have. We find the p-value or the critical value for that, and then we state a conclusion based on what we found in number 2, the test statistic, and that p-value or critical value. And in the last lecture, we talked about using this 4-step process to learn 4 new statistical tests. So in a previous lecture, we learned about the one-sample z-test, and then we followed up with the one-sample t-test when you have an inference for a population mean when sigma, or the standard deviation in the population, is unknown. We talked about the paired samples t-test, or the dependent samples t-test. That's when there's 2 dependent means, and what's the difference between those. The independent samples t-test, and the ANOVA, or the analysis of variance, and that's inference for differences between more than 2 groups. Okay, so I want you to pause the video right now and go ahead and work through each one of these. So this is just going to check our understanding based on what we learned so far. So what I'd like you to do is write out the appropriate statistical test and the null and the alternative hypothesis for each one of those. So pause the video now, and then I'm going to go ahead and do it right here on the slide and make it all messy. Okay, so you should have filled these out. I'm going to use green today because we haven't done green. Okay, so let's read number 1 and decide what test we're going to use and what the null and alternative hypotheses are. Dr. Smith wants to examine if there are differences in attendance by undergraduate year. So freshman, sophomore, etc. So it looks like that etc. means that we know there are at least 4 undergraduate years. Some do more. But the idea being that we're going to have more than 2 groups. And so that would lead me to believe that we need to use an ANOVA. And the null would be that there's no difference between these groups, right? So the mean of freshman is equal to the mean of sophomore, mean ... okay? And the alternative, of course, would be that they're not equal. Mean of freshman is not equal to mean of sophomore. I don't like green. I'm going to go to blue. Green's kind of ugly. All right, green's a good color. This green's kind of ugly. All right, number 2. We examined if our school performed differently than the district on the state test. So we're comparing our school to a district, okay? So assuming that we know something about the variance of the district, we could have this one be the one sample z-test. If we think about the district as a population from which the school comes from. So we're comparing a school that's nested within a district. So I'm going to assume that I know something about the variance or the standard deviation of the district's performance on that test. And so I can use the z-test. If I didn't, then I just had my sample standard deviation. Then I would use the one sample t-test. So either of those could work there. But the null, of course, would be that that the mu for the school is going to equal the mu for the district. All right, and the alternative would be that the mu from the school is not equal to the mu from the district. Okay? So one sample z-test, one sample t-test for that one. Okay, next one. The CEO received information that suggested that there was an income gender gap between males and females at her company. So it seems like we have males and females. We don't have any other biological category or gender identification here, so we just have the two. And they are independent samples. So we would do an independent samples t-test. And I'll just put independent. All right, and then the null, I'm going to write it over here on the side. The null would be that the mu of the income for males is equal to the mu for the females. And the alternative would be that those are not equal. Right? So it could be either way. Great. Number 4. I'm going to switch colors again because I can. All right. The statistics teacher ran through the hall screaming, they learned, and improved, and it wasn't just a fluke. All right, so we're going to assume that this statistics teacher, make a little assumption here, that this statistics teacher administered some type of pre and post test, right? It wasn't just a fluke that a class, let's say their statistics, all the classes or one class, that they learned, and it wasn't a fluke. So that teacher knew how to run a dependent samples t-test. Dependent samples t-test. And so then we could say the null would be the mu sub pre equals the mu sub post. And then the alternative would be not equal. Okay? Number 5, it looks like the diet pill doesn't work, either when it is taken alone or with additional exercise. Okay? So the way to get at this one is to think about how do we make, if we're saying this diet pill doesn't work and we have a group of folks that are taking just the diet pill and then a group's taking it with additional exercise, then we need to have also a third group, which is someone who's not taking the diet pill, right, that we compare against. So it's sort of nested within here, but here we really have 3 groups. So when we have more than 2 groups, we're going to use an ANOVA, and the null would be the mu sub no pill is equal to the mu sub pill. Oh, something happened there, sorry. Mu sub pill, which is equal to the mu sub pill plus exercise. Okay, and the alternative would be not equal to. So the alternative would be not equal to those groups. I ran out of room, sorry. All right. Our state is doing worse than the nation on the new national assessment. So again, here this could be, it looks like we're comparing a state to the nation. So a sample within a broader population. So if we knew the standard deviation for that population, it would be the one sample z-test. I'm going to change color again because it's fun. But in this case, let's say we don't. So maybe it's the one sample t. Oh man, sorry. One sample t, and so the mu sub state for the null, mu sub state is equal to the mu sub nation, or the alternative mu sub state is not equal to mu sub nation. Okay. Great. All right. Across the district, the gap between EL and non-EL students is statistically significant. So here we have one group of EL, one group non-EL. These are independent groups. So this would be a t-test again. And it's going to be independent samples t-test. So the null would be mu sub EL is equal to mu sub non. And the alternative would be mu sub EL is not equal to mu sub non. Okay? All right, the final one. The intervention improved the student's final exam score as compared with their preschool. So pre-score, I said preschool because I'm thinking about preschool. My kid's going to go to preschool. All right, pre-score. So that is going to be a dependent samples t-test because we have the same group of students. All right, so then we could do mu sub pre equals mu sub final for the null, and then not equal. Mu sub pre is not equal to mu sub final for the alternative. Okay. Sorry, that looks really sloppy as I pull back and look at everything, but hopefully you were able to work through those problems, and we can also discuss when we meet together. Okay, so a new concept that we need to introduce when we're thinking about the chi-square test is, and later when we talk about linear regression, is thinking about the idea of independent and dependent variables. In lots of textbooks, there's lots of names for these. So an independent variable is also known as the explanatory variable, the control variable, the predictor variable, the regressor, or the right-hand side variable. Whereas the dependent variable is the response variable, the explained variable, the predicted variable, the regressand, or the left-hand side variable. So we are going to think about these. I like to think of these about upstream and downstream. So the IV is going to predict the dependent variable, okay? So the independent variable explains a response in the dependent variable or the response variable. So one explains the other. So the next slide, there's a bunch of examples where we'll run through and kind of talk through which one's the independent variable and which one's the dependent variable. Okay, so go ahead and take a minute, pause the video, and thinking about this idea of which variable is going to predict or have an effect on the other variable. And the one that precedes the response is the independent variable. It acts independently. And then the dependent variable is downstream. It's going to be affected by that independent variable. So pause the video, go ahead and fill these out, try to identify which one's which, and then I'll go ahead and go through it now. All right, so let's go ahead and read through these. What is the relationship between the length of the school day and student test performance? So the question itself is just saying what's the relationship between these two. So we need to identify, well, which one's going to predict the other? Well, it seems to me like length of the school day would influence how students do on their test. So test scores are generally our outcome variables. So the independent variables, length of school day, that can vary, and it's going to predict differences in student test scores. Potentially, we're going to examine that. Okay? Some of these are weird. Sorry. Describing the relationship between cat bites and human depression using data from an electronic health record. Thank you, authors, for doing that. I think that's interesting. So cat bites seems to be an independent variable that might predict human depression. Dependent variable, okay? So whether or not your cat biting you is going to signal some change in depression, and then you might think about the mechanisms. Maybe your cat's mad at you, or maybe, I don't know, we could think of other reasons. I don't know why they're studying that, but they are. Number 3, how do charter schools impact student college going rates? So in this case, charter schools would be our independent variable, whether or not you're in a charter, and student college going would be the dependent variable. Okay. So in a lot of these charter studies, what they do is they set up quasi-experiments where the students that don't lottery into a charter school, so let's say it's oversubscribed, you have to have the lottery balls to pick students who go in. Maybe you've seen Waiting for Superman, so you have those kind of tense moments. Some kids get in, some don't. Well, the ones who don't, it's sort of like you were randomly not assigned to be in a charter school. And so you might be able to look at those students' college going rates compared to those that go to charters. So that could be a way to isolate that effect. All right, number 4, do teacher incentives improve teacher quality? So teacher incentives would be an independent variable. So that's maybe more money, recognition, time off, extra days, etc. And then the question is, does that help improve teacher quality, which would be the DV? And we would need to define that teacher quality in some way. All right, I like this one. Dogs, we did cats, so I thought we'd go to dogs. Dogs are sensitive to small variations of the Earth's magnetic field. So here's the study. Researchers carefully documented that when dogs defecate and urinate, they prefer to align their body axis with the Earth's north-south geometric field lines. So it seems like there's something about the axis, the geomagnetic field lines of the Earth's magnetic field, independent variable, which is acting on dogs in a way where it changes their behavior when they are using their bowels. So dogs are sensitive to that. So it's like the Earth magnetic field's acting on the dogs. And it's being observed in this case, how it operationalized by how they are going to the bathroom. Interesting. All right. Number 6, what is the effect of peer tutors on students' abilities to decode the reading passage? Okay, so it sounds like the effect, that's a language that seems like cause and effect. So peer tutors seems to be the IV. Sorry, I forgot to put DV here. On students' abilities to decode the reading passage would be the dependent variable. So do those peer tutors help? All right, finally one. Aesthetic value of paintings affects pain thresholds. So the study. Researchers measured the relative pain people suffer while they are looking at an ugly painting rather than a pretty painting while being shot in the hand by a powerful laser beam. All right, so there's a lot in that you have to unpack. Very interesting study. So the treatment here is whether or not the painting's ugly, okay? So instead of looking at a pretty painting, they have some condition of aesthetic beauty, which would be the independent variable. And the dependent variable is the relative pain that people feel or suffer, okay? So the mechanism, so some people get, maybe thinking about, well, what's this laser beam? Well, the mechanism to induce pain is with the laser beam. So the idea is, do you report that laser beam hurts, more or less depending on what you're looking at in terms of aesthetic beauty of a painting? Okay, so I highlighted this a little earlier, but so far we've been using this hypothesis testing procedure to determine differences between groups, and we define groups differently, how many and how they are formed. But we've been basically calculating mean differences on quantitative variables. The question is, what do we do about categorical data? So what about if we have responses to survey items, Likert scales, or yes, no, undecided? What if we have different demographic characteristics? So these nominal levels of measurement that can't be applied to some of the mean tests that we've been running before. So when faced with this situation where we do want to test for differences across categorical groups, we can use often a chi-squared test. Okay, so the chi-squared test of independence is a test that allows us to determine whether or not two variables are associated in some way. And these two variables are categorical variables. So here are some examples that we'll go through just to kind of think through this. It says, so identify the variables in the following example. All right, and I have two variables, but the first one doesn't really have two variables. That's terrible of me. But just because we've been doing the M&M example, we might want to know, is there a different proportion of one or more colors of M&Ms in a bag? And so we have a bag, and kind of like we did, we could outline, our expectation is that there would be equal representation of M&Ms in the bag. but it could be that a certain color is privileged over another. And if you drill down, maybe it's that the dyes are more expensive, or there's some reason why Mars, when they're making M&Ms, tend to favor one color over the other. And it could be that we use a series of bags. So we have bag number 1 and the colors, and bag number 2 and bag number 3. So in that way, maybe bag's a variable as well. But the idea here is just looking at color. I think these other ones will make more sense thinking about 2 variables. So the second one is political affiliation associated with perception of charter schools. All right, so the 2 variables, political affiliation, and the second one's perception of charter schools. Both of these, again, would be categorical. One might be ordinal, your perception of charter schools. I like them, don't like them, or like them a lot to really don't like them, and somewhere in between. And then political affiliation might be the party that you affiliate with, Republican, Democrat, Independent, other, or something. All right, is gender, it's usually a variable, associated with selection of an academic major. Okay, so we might have male, female, other, if we for gender, and for academic major we might have the different categories, and we could create those 2 variables. All right, is place of residence associated with attitudes towards school vouchers. Okay, place of residence might be urban, suburban, rural, for example. And then the other variable would be attitudes towards school vouchers. Again, categorical. Do you not like them? Do you really like them? Is it some Likert scale? Is it ordinal? And then what degree is that? So think about some other examples that you might have from your own research studies where you're looking at more categorical variables. This is when we would want to use the chi-squared test of independence. Okay, so as with other tests, sometimes it's just nice to run through an example and think through it, okay? So this example is political affiliation associated with perception of charter schools. And so let's say my sample is I have 180 residents, that I have their party affiliation, and it just falls into Republican, Democrat, or Independent. And then I create some contingency table that's going to record what I receive versus what I might expect, okay? And so that'll be on the next slide. Okay, these are contingency tables, kind of 2 potential results that you might receive. So I want you to ask yourself, looking through these, and I'll kind of walk through these a little carefully, but ask yourself, what is the distribution of Republicans, Democrats, and Independents in this contingency table from for, against, or undecided, all right? And what do we conclude from the patterns we find in A and what we find in pattern B? So the next slide will kind of go into that more detail, but I just kind of want to walk through briefly these contingency tables. So notice that we have 2 variables. The first variable is how they feel about charter schools. They are for them, they are against them, or undecided. And then the other variable across the columns here are political affiliation for, so Republican, Democrat, or Independent. So we have charter. And so filling this out, we have the numbers and how they break down. So 20 Republicans are for it, 20 Democrats are for it, and 20 Independents are for it. 20 are against it for each of these groups, and 20 are undecided. That's how pattern A breaks down. So we have equal representation among groups by both of the categories, okay? I want you to think about under what circumstance would that be, and what would we say about the relationship between these 2 things. In pattern B, we have 40 Republicans that are for it, 10 Democrats, and 10 Independents. Against it, we have 10 Republicans and 40 Democrats and 10 Independents. And undecided, we have 10, 10, and 40, okay? So what kind of a relationship exists here if we have, it breaking down for, higher for Republicans, lower for the others, against, higher for the Democrats, lower for the others, and undecided is highest for the Independents, okay? So how do these break down? How do we think about those? So in thinking about these two contingency tables, these two examples, they're both pretty extreme, right? Rarely do we have equal numbers of a political party in a sample. But if we were to have especially if it's a random sample, right? It's just proportionally, that's not how it's going to break down. In general, we have about 27% of the country. I think in April, 27% of the country was Republican, 26% was Democrat, and the rest were independent or other. A lot of independents, and then fewer that are affiliated with other parties. So we rarely see that kind of breakdown. But if you were to look at that table, you'd say, well, there's really no relationship here, right? It's all equal for everyone. And then rarely do we have that, right? Rarely do we have a pattern, an opinion that no one has an opinion on, especially for something like charter schools. Though we're becoming more polarized, it's rare to see individuals perfectly aligned with their political party, though it feels like in this era we generally tend to do that. But in pattern B necessarily may not be as common. So the idea would be, of course, Republicans support this idea of school choice and charters. Democrats are against it. Independents don't know. And so you saw that in contingency table B. But the idea is that both of these gives you a sense of how we can begin to look at these associations by thinking about, well, what are my expectations based on some theory or some underlying construct versus what is actually observed in the sample. And so that's how we think about doing hypothesis testing for chi-square tables. Okay, so we still need to go through the same process. So remember, our first step is always to state the null and the alternative hypothesis. So in this question, is political affiliation associated with perception at charter schools? What do you think the null hypothesis would be? Go ahead and write that down. So the null hypothesis would be, just writing it out, would be that there's no association, right? There's no association between political party affiliation and their perception of charter schools. So we have that no association. Then the alternative would be that there is an association, right? There is an association between these two things, political party affiliation and perception of charter schools. Okay, so those are both kind of extreme examples. So now I want to go ahead and make a contingency table with you. And I'm just going to kind of make this up based on percentages we know about Republicans, Democrats, and independents. If we had a sample of 180, how that might break down. And then I'll just make some numbers in terms of the perceptions of charter schools, so what we get. And the whole idea is we'll fill out this table, and then I'll give you a formula so we'll be able to calculate a test statistic, okay, which is our step 2. So I'm going to go ahead and in blue, I'm going to write down what we might expect, okay? So the expectation, if the null hypothesis was true, we know the null is that there's no relationship. So the expectation would be that they break down evenly across these categories of for, against, or undecided by Republican, Democrat, and Independent. Okay, so there'd be some kind of equal breakdown depending on the numbers. So the numbers, let me give you first, are 40 of the sample of 180. Let's say we have 49 Republicans, 47 Democrats, and 84 Independents. That roughly corresponds to 26 and 27%. And then the rest I just put as independents, okay? So that equals our total of 180. And then the idea would be, well then, if there's no difference, our expectation would be that across these, we would have equal representation. So there would be 60 for, 60 against, and 60 that were undecided. Kind of like pattern A that we had. That would suggest that there's no relationship between party affiliation and this feelings about charters. Okay? And so then we need to figure out, well, how might that break down? How might this 60 break down based on these proportions? So taking these and splitting them based on the percentages, we would have 16 Republicans that were for it. We would have 16 Democrats roughly that were for it, and we'd have 28 independents, okay? We'd have the same pattern against 16, 16, and 28. And then we would have 17 undecideds for the Republican, 15 for the Democrat. Again, that's reflecting that difference of 2 that we have down here. And then we have 28 for the undecideds. Those break down evenly, okay? So the blue here, this blue writing, is our expectation, okay? And then let's call, I'm gonna go to red. Red here is also going to be what we observe for the sample. So this is our observed sample as well. So let's say we expect it to break down this way, and it actually does break down this way. Okay, so red is going to be observed. Okay, good. So now I go out and gather my data. And I pull, let's say I just randomly sampled and I get these numbers. So I get 49 Republicans, 47 Democrats, and 84 independents, okay? And so I ask them, I say, okay, folks, how do you feel about charters? And let's say that 32 of the Republicans say, yes, I'm for it. 20 Democrats say that they're for it, and 35 independents. So if you total that, you get 87. Are for charters. 10 Republicans are against, 25 Democrats are against, and 40 independents. So that equals 75 total that are against. And then we have 7 Republicans that are undecided, 2 Democrats, and 9 independents. So that equals 18. And in that case, if you add that up, you get 180 as well. So in blue, we have our expectation based on the null being true, that there's no difference. And then the red is what I actually sample. I go out, now I made up these numbers, right? But I went out and I sampled and I got these numbers back. So those are my observed. And this is the contingency table. It's what I might expect versus what I observed. Okay, this is the chi-square test statistic. We are going to need 2 pieces of information from our contingency table in each one of the cells. So we need to know the frequency of the observed and the frequency of the expected, or the count of each of those. And so for each cell, we're going to move through this formula. And then after we finish for each cell, we'll add them all up. That's where the summation sign comes in. And that'll give our chi-square test statistic. All right, so to give you the example here, go ahead and go back to the slide if you need to and copy down that contingency table we created. But I'm going to use that information, and I'm going to start in the top left cell, so Republicans that are for charters. So I observed 32. I expected there to be 16, and so that's the formula I follow. Observed minus expected squared over the expected. And then I'm going to add that to the next cell. Well, I had 20 Democrats that were for it. I expected 16 if there was no relationship. And then for independents, I had 35 minus the 28 I expected over the 28. Okay, now I'm going to move to against. I observed 10 Republicans against, but if there was no relationship, I would have expected 16. For Democrats, I observed 25 against, my expectation of 16. And for independents, I observed 40 that were against, minus my expectation of 28. And so I put that 28 on the denominator. Now I'm going to my last row. So this is the undecideds. I observed 7, but I expected 17. And so I fill that out for the Republicans that were undecided. For the Democrats, I only observed 2, but my expectation would have been 15 if there was no relationship. And I put that over the 15. And finally, my last one are the independents. I observed 9, but I would have expected 28. Okay, and that's going to be our chi-square. Okay, and so then what you want to do is go ahead and fill out each one of these. So this one's easy because you just know it's 16. 32 minus 16, 16 squared is 256, but divided by 16 is going to get you 16 back. So we could just cross that out and say. But you would go through and fill out each one of these. So find that of all of those and then add them all up. And if you were to do that math, I get somewhere around 61.25. Now, we would stop there. That's part 2, right? We'll then move on to part 3 and 4 like we've been doing. But just a quick stop. As you were creating this table, I hope you saw that our expectation was very different than what we really had. So we shouldn't be too surprised that this number is quite large, because in lots of instances, my expectation was very different than what I actually received in the sample. And again, your expectation is based on that null that there's no relationship. So if we go ahead and have a large chi-square value, or we have large differences based on our observed and our expectation, then that'll start to suggest that within this table, just by creating the table, you realize that there's probably a relationship between political party affiliation and charter schools. So just by going through this process here, even without calculating anything, just the intuition would be, this looks really different than what we'd expect if there was no difference based on these 2 variables. So remember now for number 3, we want to find our p-value or our critical value. And we've had different distributions. Last week, or in the last lecture, we talked about the t-distributions, which look like normal distributions, but they vary depending on the degrees of freedom. Well, the chi-squared distribution is, as the squaring indicates, a non-negative distribution, or it's all positive. And you can see similarly that the degrees of freedom influences the shape of that distribution. So 1, 2, 3, 4, 5, etc. degrees of freedom, each one of those is going to create a different distributional shape. So the chart that we look to in order to find that p-value is going to be dependent on the degrees of freedom, just like the t-charts were. But this will be a chi-squared distributional chart. All right, this is a copy of the table that we can look to determine our degrees of freedom, our level of significance, and then the chi-square value that would represent that cutoff score. Okay, so we have, and I'll in the next slide tell you how we calculate degrees of freedom with this. But in this case, we have levels of significance of, if we're interested in a 0.1, we get to set that, right? That's our critical value. So we'll set either a 0.1, we've been doing 0.05, or a 0.01. But each one of those has a different chi-squared value as kind of the indicator of whether or not we would accept or reject our null. So if our chi-squared value is larger than the value we find in this table, based on our level of significance and degrees of freedom, then if our value is larger, we're going to go ahead and reject the null hypothesis. But if our value is smaller than the chi-square value we find in this table, then we would fail to reject the null. Okay, so in that table, we can set our significance level, but in this case, we need to calculate our degrees of freedom. And this is the formula that we use for the chi-square test statistic. To calculate the degrees of freedom, we take the row, the number of rows we have, minus 1, times the number of columns we have, minus 1. So go back to our contingency table, go back to that example, and take a minute, pause the video, and calculate our degrees of freedom. All right. You should have calculated our degrees of freedom. So I'm going to go ahead and do it here. We know that we had whether or not, we'll start with the rows. The rows were their feelings, perceptions of charter schools. And it was 4 against an undecided. So we know we had our degrees of freedom for rows were 3 rows. And then for our political party affiliation, we had Republican, Democrat, and Independent. We also had 3. So 2 times 2, the classic, would be 4. So the 4 degrees of freedom, okay? So that's the number of degrees of freedom that we have. And we have our chi-squared distribution. We know the critical value that we can set. And we've calculated our chi-squared test statistic. So now we need to state our conclusion. Okay, so now we get to state our conclusion. So just like the other tests, this chi-square value, if our value exceeds the critical value that we find in this table, then we can reject the null hypothesis. So let me just go ahead and draw a picture with 4 degrees of freedom. Let's say the chi-squared statistic looks something like that, okay? And we at 0.05 on the distribution for 4 degrees of freedom, if you look on that table, the critical value we set would be 9.488, and that's with a critical value P of 0.05, okay? Well, when we calculated it, we found that our chi-square value was equal to roughly 61, right, 0.25. 2425. Okay, so we're way out here, right? We're way in that tail. So if we were to calculate the p-value of this, it would be really small, really close to 0. And that's not too surprising. We know that in this case, just creating that contingency table, we saw that there were large differences between the expected and what we actually received, the observed in the data. And so since our 61 is greater than the 9.5, we go ahead and reject the null hypothesis of no relationship and say that, yes, there is a relationship between political party affiliation and your perceptions of charter schools. Okay, and I just included a link here to the Khan Academy where he goes through these contingency tables with an example as well. And so you can see the numbers kind of outlined there. I think it's good to reinforce this. So if you want more practice with this, you want a different example, go ahead and watch this video. And then when we're together in class, show you how we do this when we're in Stata.